Welcome back. This is the day the Lord's made. Let us rejoice and be glad in it. In this video, I'm going to talk about magnetism, focusing on primary transformers, focusing on AC and DC power, focusing on magnetic fields from current, introducing electromagnets, but I will have a bigger video about that later, and other just general cool stuff about magnetism. So, we're all familiar with what a magnet is. Magnetism is basically this idea that you can have unlike poles that are attract each other, or if you have two similar poles that they like each other. It comes down to magnetic domains, which we'll get to. So we measure magnetism strength in Teslas. Oops, my bad. So measured in Teslas, and we should mention too that most metals are not magnetic. Although there's a lot of people that think every single metal is magnetic, they are not. Although they can be influenced to be magnetic. All right, so iron, cobalt, nickel, those are the iron triad. Those ones are actually magnetic. Other ones aren't. So, and when I say other ones aren't, I see most of them aren't. There are definitely some other ones that are magnetic, but aluminum, magnesium, those are not magnetic. So, and it's something you've already known for a long time. Opposites attract, likes repel each other. So two south magnets repel, south and north like each other. So the Earth has a big magnetic field as well. So something that's cool to know is that our magnetic field actually fluctuates a little bit and moves around a little bit. So a cool idea is that when you look at your compass doesn't point towards true north. Your compass points towards magnetic south. All right. So when your compass is pointing towards north, it's pointing towards not geographic north, but towards where the magnetic field lines come from up at the top. So what that means is as you get close to the top, as you get close to the North Pole, your compass gets further and further off. We call that magnetic declination. So a magnetic declination is the idea that your compass is not pointing in the right direction as you get closer to the North Pole. So because, again, as you can see here, true north is what the black arrow is pointing towards, but your compass is going to be the red line. It's going to be pointing towards where the North Pole is actually as far as magnetic goes. And so you have to take into account where you're at, basically away from the equator, and determine how far off am I. So as you get really close to the North Pole, your compass is will be farther off. The magnetic declination gets larger. So what that means is if you are like in between the North Pole, true north, and the magnetic North Pole, your compass is actually pointing south to tell you to go north. So which is kind of neat to know. I should mention too, when it comes to magnetic fields, this is something we don't really fully understand is how the actual Earth has a magnetic field. But we do know that the Earth's magnetic field is declining rapidly. And so it's been declining ever since we started taking measurements back in the early 1800s. And so this actually, for those that are young Earth creationists out there, this is actually a good thing to look into to learn about this, because this is actually one of the evidences that the Earth is pretty young, because the magnetic field weakening is, if you backtrack it when it was stronger, would be suggested that life didn't exist like 20,000 years ago because it'd be too strong. So in any case, on another note though, then what old Earth people would argue for is that the magnetic field changes and fluctuates. But the problem with that is you have mass extinction every time it changes. Anything that uses the magnetic fields for long-term navigation, like a bird that uses the magnetic fields to steer themselves north or south, would die off every time it fluctuated. So in any case, this is something you can look into more, which again, I'd love to talk to you about personally too, which is a fun topic. So anyway, magnetic domains, the idea that we can magnetize something, like if you take a piece of iron and touch a piece of aluminum, you can magnetize the aluminum. You can think about the aluminum having no external field because its magnetic domains, these different regions, are not lined up in the same direction. So when groups line up with the same magnetic poles, we get a magnetic domain. So if you have random distribution, you don't get a magnetic field. But if everyone domain is the same direction, then you get a field. So magnetic fields point towards the south end of the magnet. So the magnetic pole is also where the end of the magnet would be the strongest. So, and it's just something for convention's sake to be aware of. Just like we talked about current moving, Again, Ben Franklin said, hey, let the positive move. So when we talk about current moving in physics, we're actually talking about the positive current moving usually. Although, so you want to keep an eye on, am I talking about the electrons moving or the current moving? So when talking about magnetic fields, the south end is where the field lines point towards. All right, electromagnetism. This is actually a really important topic because this is how we basically generate all of our electricity, is through electromagnetism. And so electromagnets don't work by like having some material that's innately magnetic, meaning like it doesn't have to be iron or cobalt or nickel. You can just have anything that is like a conductive metal, and you can make that conductive metal an electromagnet, and you can make it magnetic by just having electricity move through it. The general idea is, it turns out when electrons move, when electrons are moving, they produce a field. They produce a field, and that field they generate, we're going to talk about the right-hand rule here, basically is going to move around that area. So here's the general idea. If, consider this current carrying wire right here pointing straight up, and it's using I for current, and that means it's a positive current. If a positive current is moving up through the wire, as denoted here, then the magnetic field that's generated is going to rotate around. All right, so if the current's moving up, then the magnetic field that's going to be generated around it is going to be using your right hand, and that'll make some field. So what that means, if we put a compass at different places around this metal, which has current moving through it, we would have it pointing in different directions on each side. All right, so you could also, you don't need to have a current move through it to generate a field. You can also generate a field by just moving the wire through an already existing field, which is kind of cool too. So if you already had a magnetic field present and you move the wire through, that will cause electricity to move, which is, again, really important for how we actually produce our electricity in America. Now, quick note, we'll talk about this in greater detail in another video where I got to talk about the right-hand rule. But when you talk about fields being generated by electricity, magnetic fields, if it's a positive current, use your right hand. Your right is for the positive current. So if you have a negative current, like the electrons moving, use your left hand. All right, so if a positive current goes up, the field wraps around this way. If a negative current goes up, it wraps around the opposite direction. We'll talk about that later in greater detail. The idea that as a current is generated by electrons moving, this allows us to make stronger magnets, because if you keep adding more and more loops on your wire as electrons moving through, you can increase the field. So the general idea is, back to this, if you have one metal carrying some wire, you get a field. Well, what if you have multiple wires next to each other, all producing the same field? They start adding together. And so what we can do to make like really strong magnets, electromagnets, is we just use a bunch of coils of metal wrapped around, and as the electron goes through, they all keep adding in the same direction, increasing the field strength. This is pretty much what an MRI is. So an MRI is just, if you think about going into MRI, it's just a bunch of wires that are wrapped around you, current carrying wires, and when they want it to turn on, they just run a current through it. And that makes this really strong field inside there. And they can change how strong the current is, or how strong the magnet is, by just adjusting the amount of current they're using. So, all right. Now, this is actually how we get energy out of these things, and how we actually make different voltages is, I should say alternating voltages, is we can just adjust which way the electrons want to move by having something rotate inside a magnet. So, so how does a generator work? It basically is going to rotate wires in a field, which makes electrons move. So here's how it works, the general idea. And again, I'm going to look at a simulator on my next video, so that'll be going into more detail about this. If you take a magnet and you put it between a set of coils, the magnet will influence the electrons around it to move. So as this magnet moves around, it's going to cause electrons to want to move towards either the north or the south end of the magnet. And so if you keep rotating it, what happens is the electrons keep changing direction where they want to go. So when the magnet's oriented like this, what's going to happen is the current's going to move towards this direction here, towards this magnet. And when it rotates to the opposite side, then they change direction and go the other way. This also mentions too, with alternating voltages, that a lot of the time, the electrons aren't moving any direction. They actually have to come to a stop. They stop and then go turn around. And they stop and turn around again, back and forth all day. So comparing currents, we have direct current and alternating current. And direct current, electrons go just one direction. So they're just going to move one way. They provide a current that is constant, that does not fluctuate. They provide a constant power. The power doesn't change. So constant power, constant current. These are batteries. Batteries just have a chemical influence saying, hey, electrons want to go from one person to the more electronegative one. For alternating current, electrons go back and forth because we're basically rotating a magnet. We spin a magnet and electrons change which way they want to go as the magnet changes different sides. All right, so electrons move back and forth. So the current's not constant, the voltage isn't constant, and the power is not constant. So now what most devices do is they have a diode to make it turn into direct current. But for transporting energy, we use alternating current. USA, we got 3 wires at your house when you plug something in. Generally, one of those is ground, which is 0 volts. Then the other ones are plus or minus 120, so they're out of phase. So now we should mention, though, that when we say plus or minus 120, that is like an RMS, which pretty much you can think of as like average. They're not the exact same. Root mean squared, whatever. All right, so the general idea is we actually peak higher than 120. So the peak voltages in America are roughly like 170, but what you average ends up being about 120 for the voltage of the motivation you're getting. We also have these things out of phase rotating. So basically we spin the magnet at 60 hertz. All right, so if the magnet spins at 60 hertz, we get a frequency of 60 hertz. So that's what's going on there, is we're just constantly making electrons change direction. The reason, I should say, one of the reasons why we like to use alternating current is because we can step up and step down the voltage using basically magnetic fields or electromagnets to increase that by having just multiple wires wrapped around. As far as you need to know, just transformers are something we can change the voltage on. The way they work is we just change the number of coils on different sides to step up or step down the voltage. And so a transformer, and there's probably one of these around your neighborhood somewhere, all it is on one side of the transformer, there's more wires than the other one. And the voltage is proportional to the number of wires, because every single time you add another loop, you're increasing the strength of the field. And so to change the strength of the field, you just change how many wires you have. So what generally happens is at the power plant, they step up the voltage so that going across the country, we have these high voltage lines, and then they step it back down to what you're going to use. So the equation for figuring out the voltage is it's a proportion, where the V for here stands for voltage and N stands for number of loops, number of coils. So if you have 10 times the loops, you get 10 times the voltage on the other side. This is also kind of neat to know, is the energy that goes from the power plant to your house is not along a continuous path, as far as there always has to be a metal between them. Like, it's not a continuous circuit in the way you would normally think of it. So these loops here, these wires, don't connect to these wires physically. So there's a field that gets generated, and that field influences this field over here to cause electrons to move. Again, that's kind of a neat thing to think about too, is we don't actually have a continuous metal line going there. So low voltage on the low number of loops, high voltage on the high number of loops. And we use an iron core just to kind of direct the field, but this is the general idea. So again, what's going to happen is the power plant is going to spin a magnet. That magnet's going to then produce a certain voltage. And then we're going to use a series of transformers to step up the voltage, and then we're going to step it back down and then distribute it out to different places. One more thing I forgot to mention. Let's go back to real quick with, must have been somewhere else here. Oh, right here, sorry. One more thing to mention is, so not every single device in your house runs on actually 120 volts. Some devices run on a higher voltage than 120, probably like your dryer, it has like a special hookup. Your stove probably has a special hookup. And so typically when you plug something into your wall, it hooks up to a ground and just one of the plus or minus 120s. So you get 120. But if your dryer, which needs more than 120 volts, which runs on 240 volts, what it's going to do is it's going to hook up the plus and the negative 120s together, so you get the bigger voltage change. All right. I will talk more about electromagnets in a subsequent video using a simulator. God's peace.